Thank you very much. And in the immortal words of Monty Python, and now for something entirely different. I would like to pause and thank John Milner for bringing me into a field which I had absolutely no interest in beyond eating badly. He convinced me that I ought to be thinking about how these new technologies would be used and abused in a variety of settings. I come at this from a very different and perhaps orthogonal view from most of the people in the room. We were funded a while back by DARPA to address a simple problem. There was a time within living memory in which pharmacists in the basement of hospitals would have to take an antimycotic or an antibiotic which was highly hydrophobic and get it into a drip bag, and by vigorously shaking using mechanical means, make suspensions that were variably stable. A pharmacy tech would then run the drip bag up into the cancer patient's ward, hang the bag as quickly as possible before the emulsion broke. And what was delivered was this heterogeneous set of bubbles of oil and water that were very painful to administer and would have very complex pharmacodynamics and pharmacokinetics. So we came along, and in keeping with the idea of nutrition and food, we began to make smart Italian dressing. It's something that you've done while waiting for your meal. You have an immiscible bottle of oil and water, and if you shake it up, depending on the proportions of oil and water, you'll make a bubble of water in oil or vice versa. If you can stabilize that bubble, and by the judicious use of surfactants, a process that is more art than it is scientific, by understanding things like cloud points and so on, you can stabilize that bubble of oil and water, and now you have the beginnings of a self-assembling structure. You then allow the forces of nature to take over, and if you add hydrophobic materials, they will arrange themselves in a preordained fashion in that bubble of oil. And by adding the right ingredients, you end up with, in this case, a garlic Italian dressing. It's prettier than that, though, because it's very simple to do, and we have undergraduate students doing this in our labs. This is the sum total of the equipment that we use to make these smart powders that can be completely naive, i.e. untargeted, or targeted specifically to brain tumors. You simply set up your emulsion either at room temperature or slightly heated or cooled, depending on the chemistry. You wash, you filter, and then you launch the material into the vehicle of choice. What you end up with is a very uniform set of particles that can be made of polymer or some polymer matrix in which is embedded the active moiety, a drug, or for the purposes of this symposium, potentially a fortificant or a nutrient. You can then, in fact, target the surface of this to any tissue that you want, and you can see here you have moved now from some random set of pharmacodynamic properties into a more uniform set. The problem is that the dose metrics, once you get below 100 nanometers, are incredibly complex. At below 100 nanometers, we are in the space between Newtonian physics and quantum dynamics. And it is precisely because of this scale that our bodies work. It is because our enzymes and the motors of life are in this space that you get the benefits of bulk motion and of quantum mechanics. And so reactions that are not favored in the bulk happen at the nanoscale. with respect to the delivery of a material into the biological space, one of the issues that arises is that surface area increases exponentially the smaller that you get. And so the probability that your nanomaterial will interact with something in the biological space goes up exponentially. And I'll show you an example of that later. It also means that the number of atoms on the surface as a property of the material goes up exponentially. Let's put this into a concept that you maybe can grasp a little more easily. If you grab a 1 kilogram iron cannonball and grind it down into 100 nanometer diameter particles, the surface area of these 100 nanometer iron particles is 10 to the 8th times larger than the cannonball itself, which means for the same mass, you have an enormous potential for interaction with the environment. So we've heard a great deal of talk about the right side of that dose-response curve. What makes nanomaterials toxic? We know that high aspect ratio, so things that are long and thin, like asbestos fibers and something that's been in the news quite recently, carbon nanotubes, are probably not the best way of getting a nutrient into the body. And that is because these long fibers get picked up by macrophage, and it's a bit like you trying to swallow a javelin. You just can't do it. And so you walk away and leave it behind, and another macrophage comes behind, and you get successive waves of inflammation. Biopersistence. And here, again, we've moved from a chemical, lipophilic or hydrophilic, that moves with the distribution of water or lipid in the body to something that has object permanence and can stay in a 3D location somewhere in your body. If that stays there for a long time, again, it can interact with the immune system. Anything with reactive surfaces and points capable of producing reactive oxygen species, and we now know that for a number of nanomaterials, if you add a redox-capable transition metal, many of which have nutrient value, you add to the toxicity of the nanomaterial. Here, though, composition, chemical composition, is in equilibrium with the ability to persist. So these quantum dots, which are beautiful and great for tagging all sorts of things like tumors and tissues and so on, are typically made of things like cadmium, selenide, arsenic, and so on. And if you have that stay intact in small volumes, that's okay. However, at biological pH and salt concentrations, these particles dissolve. And what you've done then is delivered a supraphysiological concentration of those materials in a tiny space. And you no longer benefit from the bulk phenomenon of volume of distribution. We learned this from manganese in welding fume, where welders who were in very confined spaces would get what was called fume fever. They would inhale large amounts of nanomaterial. Their interleukin B1 would go up, or interleukin 1 would go up. They would get fever. You'd send them home, leave them alone for a couple of days. They would come back just fine. Unfortunately, those that had high doses developed manganism and Parkinsonism, a form of Parkinsonism. Coatings will change your pharmacokinetics and pharmacodynamics. There are a wide variety of materials that are used in the pharmaceutical industry, including dextrans, dextrans on the surface of silicas, titanium dioxide, zinc oxide, and polyethylene glycol and so on, have been used to passivate the surface of nanomaterials to reduce the toxicity and to aid with the delivery into a specific specific site. This is the part of the talk where I actually go against the title of the talk and stand on my soapbox and say, there is no such thing as nanotechnology. It is the only field in biomedicine in which we define one dimension, being less than 100 nanometers, as the defining characteristic. And in fact, the size really doesn't matter, and I'll show you why in a moment. One of the most exciting areas, I think, with respect to the foregoing talks is this emerging idea of the band gap energy, which occurs and is absolutely pertinent for those materials that are metallic, bimetallic, or metal oxides that may have value in delivering micronutrients. What am I talking about? Just a little physics on a Saturday morning. If you take any crystal, any metallic crystal below typically 10 nanometers, and it has this periodic latticework structure, there exists a gap in which electrons cannot exist. Those of you that remember your organic chemistry will remember in the molecule, this is referred to as the distance between the highest unoccupied, or highest occupied molecular orbital and the lowest unoccupied molecular orbital. And it's the dancing back and forth of electrons in this area that gives us fluorescence. The problem is that in oxygen, fluorescence leads to photobleaching because that electron is easily diverted off onto oxygen. As the material gets more and more confined and more structured, you get this band gap energy, which is very stable, which is between the valence band, i.e. the electron simply wandering off and giving you a plus sign on the nucleus, and the conduction band, i.e. the ability of that electron then to wander through the material, and so you get a semiconductor. Well, this band gap energy concept was first harnessed by Xiumin Yi when he made these beautiful quantum dots. And the different colors that you see are merely a reflection of the size of the particle. And this is now being used in a wide variety of products and in the tagging of various biological tissues and so on. But as a general principle, the density of the state, as it increases, widens this gap between the valence band and the conduction band. So this very same chemical identity will give you a band gap that actually has a biological significance. Andre Nell and his colleagues at UCLA did a fabulous series of experiments in which they arrayed a variety of metal oxides by band gap energy, measured the band gap energy, and saw that as they came through titanium oxide, aluminium oxide, copper, and then there's manganese oxide on this right edge of it. This band, which has a band gap energy that overlaps with this hydrogen-proton coupling, coincidentally, the energy gap that is favored by the production of singlet oxygen and superoxide in biological conditions. These metal oxides produced toxicity. And so there has been talk about zinc oxide, and other zinc sulfates and so on, which are insoluble salts of zinc and therefore have to, in aqueous solution, form clusters. And in order to remain in suspension, must be in the nano range. So depending on the formulation of these crystals, I would posit, many of them may overlap in this band gap energy range and interact adversely with macromolecules. Moreover, because of the enormous surface area, nanomaterials are really sticky. And so in order to go from, in the simple example, a C60 fullerene, which does not suspend in water, we simply add a bunch of hydroxyl groups on the surface. This is water-soluble and much less toxic. Vicky Colvin and Christy Sayes were the first to show this. Depending then on the polarity of the surface, you can get these nanomaterials to interact with phospholipid and with other biological macromolecules. If they're highly hydrophobic, they'll stick to highly hydrophobic materials in the cell, hydrophilic, and they'll stick to highly charged groups. And so you cannot predict a priori where your permanent object is in the biological space. The more permanent it is, the more likely it is to interact with that material and cause a potential issue. It could be a beneficial one, or it could be an adverse one. We took a very simple hydrogel, absolutely no reactivity on the surface that we could detect using classical analytical chemistry techniques, shook it up with plasma, and a whole variety of things, a couple of which we simply couldn't identify, stuck to the surface. These are all biologically active molecules. And so by aggregating these onto the surface of a nanomaterial, you set in motion the potential for a number of unanticipated signaling effects. That doesn't mean that it's toxic. So we took that very same hydrogel material and we subjected a series of poor rats to this ungodly amount of hydrogel in their blood, half a gram per kilogram. It's a huge osmotic load, but there was absolutely no pathology in the major organs. If we added superparamagnetic iron oxide nanoparticles, which also dissolve at physiological conditions, under physiological conditions, and provide iron as a nutrient source, we get, at high concentrations, rapid necrosis of the renal cortex and petechial hemorrhage in the liver. So dose really does matter. So let me go to some claims that I've seen, and I, in the interest of good taste, didn't put any particular product up on the screen. But nanomaterials are smaller than the wavelength of visible light, by definition, which means that you can't see them. So these simple carbon nanotubes are invisible to the naked eye. But there are a couple of fortified waters out there that claim to have nanonutrients in them. I urge you to go up to them, look at the bottom of the bottle, and you will see precipitate. Because nanomaterials are unstable wherever there's moisture. So if you take beautiful, pristine carbon nanotubes, shake them up in air with any water in them, it, i.e. humidity, they will clump. And so the claim and the additional price of a nano product may be completely obviated by the fact that it's now clumped into big, unabsorbable chunks. We have also evolved in an environment that is absolutely full of nanomaterials. This is how our immune system evolved. So if you take a low concentration of a benign hydrogel, simply launch it into blood, and look at the immune system, these are just macrophage. Here we made our particles pH sensitive, and you can see how beautifully these get taken up by endosomal activity. So any free nanomaterial that comes in contact with the immune compartment is rapidly removed. And over time, this compartment gets acidified. So you can see over time there are more nanoparticles and the pH gets lower. That means that that particle is constantly changing as the pH changes and the surface chemistry changes. This was posited by the folks at CBEN at Rice University to be a good thing, that once you gave, and this is a nanomedicine application, once you gave these particles intravenously, they would be accumulated by the liver and potentially detoxified. Well, we took a look at it, and we used fluorescent nanoparticles, and indeed it goes to the liver, but it doesn't go to the liver homogeneously. The nanoparticles end up in the Kupfer cells. And these Kupfer cells are evolved to pick up particulate matter that escapes the gut. Their job is, after there is breach of the gut epithelium and the passage of nanomaterials and microscale materials, to clean up the blood through the mesenteric flow so that these particles don't get distributed more broadly. Eventually, though, there is shuttling of these cells between the spleen and, we now know, the bone marrow. So over the course of about 42 days, this material gets shuttled very carefully from the liver, the sinusoidal surface, to the spleen, and ultimately into the bone marrow. But here's something that puzzled us when we did the first experiment. We chased radioactively labeled nanomaterials around the body, and they ended up in the usual space. But there was a large fraction that we couldn't account for. So we looked at the interstitial space in the animal. And as our model predicted quite nicely, as we increased the amount of nanomaterial, this expanding light gray area here represents the interstitial space. Because as nanomaterials move through the bloodstream, there is an outward pressure in the capillary bed of about 0.3 millimeters of mercury that pushes materials like nanomaterials through the fenestrations in the blood vessel and causes them to accumulate in the interstitial space. If they are osmotically active, it causes an effect called third spacing, in which water will move into the interstitial space. So, with more direct relevance to food, already nanomaterials are being used as coatings on things like apples, as antioxidants to prevent the browning of cut fruit surfaces and so on, and as micelles and lipid bilayers or monolayers for a variety of purposes. That material is then under the influence of a variety of macro and micro environments, including the effect of saliva in the mouth. It then takes an acid bath in the stomach, gets immediately immersed in bile, and then becomes in direct contact with the complex microbiological environment in the gut. We know nothing about these interactions scientifically. There's a little bit in the literature, but we have no idea how these materials interact with the gut. In fact, Nanowerk in Germany produced a list, which is now widely distributed, of the most common food-related applications, and they go all the way from field through to supplements. Let's take a brief look at why there may be no problem and why there may be a very big problem. And the answer is, I think, appropriately left up to the science that should be done. If we look at the epithelial barrier in the gut, in the intestine, there are dendritic cells that send out an arm into the lumen. They constantly interact with bugs in the lumen, there is a paracellular interaction between B cells and dendritic cells and signals that go to the proximal mesenteric lymph node. All of this interaction results in the regulation of secretion of IgA from the gut epithelium. The introduction of engineered nanomaterials into this interaction is not well understood. The M cell, or the microfold cell, forms a similar interaction by sampling the gut microflora and schooling the gut-associated lymphoid tissue. But we do know that anything that causes a disruption in this interaction and results in the elaboration of pro-inflammatory cytokines will feed back and disrupt the tight junctions in the gut epithelium. So, as we've spoken today and had this conversation about food fortification, we have implicitly provided a picture in which we administer a fortificant to somebody who's healthy or deficient. But I would like to flip the script a little bit, because there exists in our population a wide variety of pre-existing morbidities. So, if we just look here at the CD4 competent immune cells that line the gut of this normal individual, and the picture over here in somebody who's infected with the human immunodeficiency virus, you can see that the physiology here, the cytokine cycling is going to be very different, and the interaction of a nanomaterial with that immune system is likely to be different. So, in summary, we need to learn a lot more about what dosimetry for nanomaterials means. It's not simply the concentration of the fortificant or supplement in solution that we need to understand. We need accurate quantitative methods for measurement of nanomaterials in complex materials, and because of the constraints of time, we weren't able to talk about how they behave in hydrogel materials and other complex environments. We know very little about the long-term stability of these materials, and we have very little, although emerging, database on the absorption, distribution, metabolism, and excretion. The impact of materials on non-pulmonary or dermal immune systems is not fully known, and we need to really gather a great deal of information on both the acute, subacute, and chronic interactions with the immune system. With respect to gastrointestinal tone, we know nothing, and we need to find that out quickly. In the end, I would like to thank the organizers for the invite and remind us all that if we don't get these questions right, all of these fine technologies will end up in the nano potty. Thank you very much.